Hello, so today we are going to be talking about the adiabatic flame temperature of a steady state system. So we are going to start off with a little picture here. So let's say that this is a lighter. We are going to have air and fuel going into this lighter, and then we are going to get a flame that comes out. So all a flame is hot gas. So looking at this, we have our temperature going in is equal to 298 Kelvin, which is our stated temperature in, and then our T out is going to be some temperature, so we are just going to call that T. So now, to find the temperature that is coming out, we are going to compare the change in mass of the system, and this is going to be in relation to the internal energy, the kinetic energy, and the potential energy of the system, all with respect to time. This is going to be equal to what's coming out of our system, so the change in mass times the enthalpy plus kinetic energy plus potential energy, and this is what's going in. So this is our total system. So we are going to start with what's going in, and this is in respect to time, and then we are going to subtract the change of mass, or the change in mass, the enthalpy, and the kinetic energy, and the potential energy that is going out of our system. And this is also with respect to time. So now, if we are looking at our situation here, we can see that it is adiabatic, so there is going to be no change in mass at all in our system. So we can cross all of those out. The energy inside of our system is not going to change since it's adiabatic, so all of these can be crossed out. So what are we left with? We are left with 0 is equal to enthalpy in minus our enthalpy out as all that we're left with. So now we can say that the enthalpy in is equal to our enthalpy out. So now we are going to look at the heat of formation of our system. So we are going to have the heat of formation that's with respect to the temperature is equal to the heat of formation of our initial temperature this is the heat of formation of our initial temperature, and we are going to add the integral of 298, which is our initial temperature, to T, and then we're going to look at the heat capacity, and then this is going to be in respect to time. So now we're going to go and look at the ChemCAD equation 107. Okay, so we are going to start out here by looking at the ChemCAD equation 107. So this is already given to us. So this equation is y is equal to a plus b times c divided by t divided by the hyperbolic sine of c divided by t, and that's squared, plus d times e divided by t divided by the hyperbolic cosine of e divided by t, and that is squared. So now if we look at integrating this equation, integrating a is going to be easy. That's just going to be at. But then if we look at integrating the b term of our equation, that's going to get a little more complicated. So we are going to go over to Wolfram alpha, and we are going to take the integral of, of c divided by t, and then divided by the hyperbolic sine of c divided by t. This is all going to be squared. Oh, we need one more parenthesis in there. And then this is all going to be squared, and then we are going to take all of that with respect to t. So we are going to hit enter, and we are going to get c times the hyperbolic cotangent of c divided by t plus a constant. So now if we look at the other portion of our equation, we are going to just open up another tab here, or I can do it twice, and we are going to take the integral of the second part of our equation. Is going to be e divided by t divided by the hyperbolic cosine of e divided by t. All of this is going to be squared, and we're also going to take this with respect to t. So this is going to give us, so the negative e isn't actually our term. Wolfram alpha just always turns the capital E into an E. So we are going to get e times the hyperbolic tangent of e divided by t plus a constant. So now if we go back and look at our equation, we are going to get y is equal to at times b, or plus b times c times the hyperbolic cotangent of c divided by t, and then we are going to get plus d times e times the hyperbolic tangent of e divided by t. So now we are going to go back to the whiteboard. Okay, so now we're going to look at the stoichiometry of our combined fuel. So we know that our fuel is going to be methane, which is CH4. So it's either going to be methane, it's going to be ethane, which is C2H6, or it's going to be N-propane, which is C3H8. So now looking at this, we have to add in our oxygen. So we are going to do plus O2, but since we are actually using air, not just pure oxygen, we have to add in nitrogen. So we have N2. Now this CH4 and the O2 is going to react to produce CO2, which is carbon dioxide, and it's going to produce water, so H2O. And then we have to add nitrogen on this side too, but that is not going to form any products. That are just going to stay nitrogen. So we're going to rewrite this for our other two. It's going to give us these same products. All three of these are. And give myself a little room right here. Okay, so now we are going to balance these equations. So we have one carbon and one carbon on the other side, so carbons are good. But we have 4 hydrogens and we only have 2 hydrogens on this side, so we need to add a 2 in front here. So we have 4 hydrogens on both sides, but now we have 4 oxygens and we only have 2 over here, so we have to multiply this by 2. Now, for nitrogen, air is made up of 79% nitrogen and only 21% oxygen. So for the nitrogen, we have to have 79 over 21, but then we also have to have the same amount of nitrogen that we do oxygen. So we are also going to multiply this by 2, since we have to multiply this by 2. So now in our next equation, we have 2 carbons on this side. We only have 1 carbon here, so we're going to have to add a 2 in front. So we have 6 hydrogens and only 2 over here, so we need to add a 3. So now we can see that we have 4 oxygens here and 3 oxygens here. So we have to multiply this by 7 divided by 4. And now, looking at nitrogen, we have to do the same thing, 79 over 21 times 7 divided by 4, and then 79 over 21 times 7 divided by 4. Moving on to our next equation, We have 3 carbons on this side and only 1 on this side, so we have to multiply by 3. We have 8 hydrogens on this side, 2 on this side, we have to multiply by 4. So now we have 6 oxygens and 4 oxygens, so we have 10 oxygens on this side, so we have to multiply this by 5. We're going to do the same thing we've been doing for nitrogen, 79 over 21 times 5, and 79 over 21 times 5. So now we are going to go and code this in Colab. Okay, so now we are going to start looking at our Colab. So this first section right here, this is just importing a file from our GitHub that is going to let us use CHE tools. So if we go inside CHE tools, we can see all of these different chemical compounds and all of the properties of them. So if we take a look at ethane, today we are going to be using the ideal gas heat of formation, and as we can see here, the units are in kilomoles. So we are going to have to divide by 1,000 to get it back into moles. So still looking inside this ethane properties, we are also going to use this ideal gas heat of capacity. And these coefficients for that property is what we're going to be using. So this is A, this is B. So this is going to, so those coefficients are related to our ChemCAD equation, and they are going to give us our coefficients of A, B, C, D, and E. Okay, so now we are going to start setting up our Colab here. So we already imported NumPy, and we imported the root function from SciPy, and we also imported tools.che. So the tools.che just lets us access our CHE tools that we already imported up here. So now we are going to initialize our prop, and we are going to set this equal to che.props, and we are going to pull methane, we're going to pull ethane, N-propane, oxygen, we're also going to pull nitrogen, carbon dioxide, and water is going to be our last one. Alright, so now we are going to start looking at the amount of carbon and hydrogen that is inside our fuel. So we are going to have fuel underscore carbon and hydrogen is equal to this array. So we are going to have 1 carbon and 4 hydrogens in methane. We are going to have 2 carbons and 6 hydrogens in ethane. And then we are going to have 3 carbons and 8 hydrogens in propane. So now we are going to find the moles, or we are going to initiate the moles of our fuel. So we are going to say, we're going to create an array, so np.array. And we are going to say that we have 10 moles of methane, 1.5 moles of ethane, and 1 mole of propane. What did we do wrong? So the problem that we had is I had an extra period here after the 1.5, so that was supposed to be a comma. Okay, continuing. So now we are going to find the number of moles of carbon that we have and the number of moles of hydrogen that we have. So we are going to do this by taking N fuel and multiplying that by the fuel underscore CH underscore S. So that is going to give us the number of moles of carbon and hydrogen that we have. So now we are going to find the number of moles of carbon dioxide. So that is just going to be NC because that'll give us the number of moles of carbon that we have, and carbon is our only coefficient or our only term that has carbon in it. So now we are going to find the number of moles of H2O, which is water. So we're going to have the moles of hydrogen divided by 2. Now we are going to look at the number of moles of oxygen that we have, and this is going to be NC plus NH2O, H2O, and then we are going to divide this by 2. Now we are going to look at the number of nitrogens that we have. So as we said on the whiteboard, the composition of air is 79% nitrogen and 21% hydrogen. Or 21% nitrogen, sorry. 79% nitrogen, 21% oxygen. My bad. And then we're going to multiply this by the number of moles of oxygen that we have. Now we are going to get into finding the number of moles that we have going in. So we are going to use the function np.concatenate. So I can't say it, I'm sorry. We're going to use that function to combine arrays here. So we're going to make one array out of our N fuel. And now we are going to create a new array, so numpy.array of our values of we're going to create a new array of our values of our moles of oxygen, and then our moles of nitrogen, and then we are also going to do carbon dioxide and water, but starting out we have no carbon dioxide and no water in our system. So now we are going to look at the number of moles out, and we are going to use the same function to combine arrays here. But we do not have any fuel left in our system, but we still want an array that is going to give us the same amount of values as our fuel did. So we are going to do np.zeros. So this is just going to put 0 in. And we are going to do underscore like, and we are going to call our N fuel. So this is just going to make sure that this array has the same amount of values that our N fuel did. So now we are going to also create another array just like we did in the last step. Actually, I'm going to put this on the next line. And we are going to do np.array of, so now we have no oxygen left in our system, so we're going to have 0.0. We are still going to have our nitrogen, and now we have our moles of carbon dioxide and our moles of water. Shift enter on that. Now we are going to start looking at our sensible heat. So we are going to define this as delta Hij of T, and then we are going to return, we have to use this formula. We're going to use our formula from ChemCAD, but we have to use prop dot the heat capacity of Ig, and then our variable A, and then we are going to multiply this by T, so that is our first part of our equation, and then we are going to add B, oh no, we have to do our prop again, so we are just going to continue to copy and paste this part of it. So we are going to do prop, but we are going to change A to B, and then we are going to multiply this. Oop, that is not what I wanted to do. We are going to multiply this by C, and then divide by NP dot the hyperbolic cotangent of C divided by T, And then we are going to subtract D times E. I'm going to put this part down on the next line. I don't like it being that far. Okay, so then we are going to subtract D times E divided by the hyperbolic tangent of E divided by T. So now we have to divide all of this by 1000. As I said earlier, the property of the ideal gas in our CHE tools is in kilomoles, so we have to divide by 1000 to get it into moles. So now we are going to define an equation of heat formation. So we are going to define HFIG, and this is going to be in relation of the moles and of temperature. So now we are going to return a dot product, so NP dot dot of the moles, comma, prop HFIG, and then we are going to add the NP, so we're going to add the dot product of N, comma, delta HIG of T, and we are going to subtract the delta HIG of our initial temperature, which is 298 Kelvin. So now we can find our energy balance equation, and we are going to define energy balance, and we are going to make this a vector. So we are just going to do V. Now we are going to find our temperature out, so we are going to have the temperature is equal to the array, or the vector, of 0. And then we are going to return H, the heat formation of the ideal gas of NN, comma, 298. Oop. Didn't have my numlock on. 298, and then we are going to subtract the HFIG of N out, and now we are going to use just T because that's the temperature that we're looking for. So earlier we imported this function root, so now we are going to use that function to find the roots of our equation. So we are going to do root of energy balance, and now we have to make an initial guess of what our temperature is going to be, so we are just going to use our initial temperature. Okay, so I went back through our code and found our problem. So right here I had just prop HFIG. It is supposed to be prop dot HFIG. So we're going to rerun all of these. Now we have another error. Okay, so for our second error, NumPy does not have the hyperbolic cotangent, so we are actually just going to use up here, we are just going to use tangent, not cotangent. So we are going to rerun these. Okay, so for our third error, we have a division symbol here, and this needs to be multiplication. Oh, also, we do not have np.tangent here. So finally, after a few errors, we got through it, and we can see that our final temperature of our flame is going to be 2,717 Kelvin. Thank you for watching.